Hello, so in this video we will talk about regular expressions and regular sets. So as usual, it starts with the definition. So the definition turns out to be a recursive definition. So we define it as follows. So we say that the symbol null set expression is a regular expression. The symbol lambda, which represents the empty string, is a regular expression. Any symbol that is a regular any symbol is a regular expression if it is a part of the set we are talking about. So when we say regular recursive definition, we are defining it over a finite set I. Okay. So and then if A and B are regular expression, then AB, which is a concatenation of A and B, this is a regular expression. A union B is a regular expression, and A star is what? The Kleene closure of A is also a regular expression. Okay. Now each regular expression corresponds to a regular set, and these terms are used interchangeably. So whenever we talk about regular sets, it means that it is a set which is corresponding to a regular expression and vice versa. So each regular expression corresponds to a regular set here. So this corresponds to an empty set. Naturally, this corresponds to a set which only has one string, which is the empty string. This X symbol corresponds to a set which has only one symbol, which is X. And then AB corresponds to the concatenation of the sets A and B, and A star corresponds to the Kleene closure of the set A. Okay, so this is, you can see that the language is the same, but sometimes regular sets mean um, all the and all the elements which corresponds to an expression here. Okay, so now let's go to the interesting part here, when we have to do we have to express a regular set in words. So this is a regular set. We have a string 111 and we have a string 000 and we have a union here. So this is straightforward. So this is a string of 111 or 000. So this is straightforward. Now this guy is what? Now this guy is a little bit tricky here. So let's do it here. So here we have 00 Kleene closure, 1, and then Kleene closure here. So this means what? Put this one first. So we have a 0 followed by 0 or more zeros because of Kleene closure of 0, then followed by a 1. Okay, so this is what it means. Then we have 0 or more strings of the above type. But then this is not very interesting, right? I mean, this is what we have translated this into English here, but we want the reader to know that this means this means some, there is a pattern here, or this means some specific type of strings we are talking about here. So what does it mean? 0 followed by 0 or more zeros followed by 1, and then we have 0 or more strings of this type. So let's take some examples. So 0, 1 is one example, and obviously empty string is another example. So 0, 1 is another example where I have no zeros, and I'm just taking the one, this Kleene closure, I'm just taking the one part of it. Okay, and then I can have 0, 1, 0, 1, and then I can have 0, 1, 0, 1, 0, 1, and this is it. But then I can also have 0, 0, 1, I can have 0, 0, 1, 0, 0, 1, I can have 0, 0, 1, 0, 0, 1, 0, 0, 1, and so on. So I can repeat 0, 0, 1 infinite number of times. I can repeat 0, 1 infinite number of times, and similarly I can repeat 0, 0, 0, 0, 0, 1 infinite number of times, and I can go on and on and on. So now I can see a pattern. So what is the pattern here? The pattern is that it is a set of strings which always ends at 1. So this is the first observation, always ends at 1. What is the second observation? The second observation is that between every two ones there has to be one or more zeros. So between every uh, pair of ones we have at least one zero. Okay, so now this is more interesting now. So this means that this guy represents a set of strings which always ends at 1, and between every pair of ones we have at least one zero here, and obviously we have to say always also contains an empty string. Okay, so this is about this guy. So now you can see that this is more interesting. I mean, this is also correct, there's nothing wrong with it, but for us this part is more interesting, that we have to generate a set of strings which have some roots. So this is more compact way of saying this story here. Okay, okay, now we have to check if this string belongs to this regular set. Okay, now this is easy to see. Why? I can say no immediately because I can see that this always ends at 1 1. Okay, and this ends at 1, so this is a no. Okay, but this, so these kind of questions are easy to see because we can immediately see, usually we can immediately see whether the answer is yes or no. Okay, now we are doing the opposite way. Now we are given a set, we are given some rule or some set of rules, and we have to find a compact expression using a regular set for a given rule. So let's start with set of strings of odd length. So odd length. So odd length means what? So first of all, I can have just 0 or I can have 1. And then I can have all the combinations for length 3 strings. So can I have 0, 0, 0, 0, 0, 0, 0, 0, 1 and up to 1, 1, 1. Then I can have all the combinations of length 5. So which is 0, 0, 0, 0, 0 up to 1, 1, 1, 1, 1. So I can list down all the odd numbered odd length strings. But again, this is not very interesting because we want a compact expression like this. So what do? We do something like this. We say we can have 0 or 1. This is always the case, right? Because we have all odd strings. Then we can say 0 or 1, 0 or 1, and clean closure of that. So we can have an empty string here, but 0 or 1 will be here. But we can have any string of length 2 here. So this is length 2 strings. Length 2, not length 2, even length strings. So even length strings. So it should be like even length strings. Okay. So then this is even length strings preceded by a 0 or a 1. And actually you can put this 0 or 1 in the end as well. So you can also say 0 or 1, 0 or 1, and then 0 or 1. This is also correct. Okay. So this is about odd length strings. So let's do this guy. So set of strings with exactly 1, 1. So then we have a 1 here. Then we can have any number of zeros here. And then we can have any number of zeros here. Okay. So this is straightforward. So you can see that some of them are straightforward. Some of them we need a little bit of work here. But then I think you all will agree that this guy is also correct. But this guy is more interesting and more compact way of writing the same thing. And you can see that just a simple definition like recursive definition which comes very natural to us can lead to something which is beautiful and very compact. Now set of strings with this number of ones followed by an even number of zeros. So this number of ones we can say what? We can have 1 1 and then 1 1 1, correct? And then we can have followed by an even number of zeros, so 0 0 and 0 0. Now here I'm assuming that even number of this even 0 is not an even number, so I have 2, 4, 6, 8. But if you assume that 0 is also even, so you can say or 1 1, the number of ones will not change, and then you can say, so here it's an empty string. So now we can have a string with no zeros, but here we can have a string with at least 2 zeros. So this is it about how do this is about regular expressions and regular sets, and how do we go from a set of strings to a compact expression using regular expression, and how do we go from a regular expression to a set of strings uh, which define those expressions. Okay, so hope it was easy to understand, and thanks for watching. Hope you liked the video.